To analyze an indeterminate structure, we can use force methods, which basically assume redundant forces. And the number of redundant forces has to be equal to the degrees of indeterminacies. As you know that for actual structure, the degrees of indeterminacy can be really high. So that brings very complicated situations into your analysis. So in this part, I will introduce another method called slope deflection method. This method uses deformation as an unknown. So the deformation could be displacement or rotation angle. And these deformations are called degrees of freedom. So note that the degrees of freedom does not have to be equal to the degrees of indeterminacies. So to define degrees of freedoms, we need to note elements and nodes. So let me use this structure as an example. This is a clamp beam on the left, and on the right is a roller support. So if I model the whole beam with only one element, at the ends of the elements, I call them nodes. So I call node A and node B. So the degrees of freedoms or the deformations of the structures are associated with the nodes. For instance, at node A, it's clamp end. So there's no displacement, no rotation angle. At node B, it's roller support, so there's no displacement, but there's a rotation angle. So this rotation angle is called degree of freedom. So as a result, if I model this beam by one element using two nodes, then I will end up with 1 degree of freedom, which is theta b. I can also model the same structure differently. For instance, if I model this beam using two elements, so I call element 1 and element 2. So at the ends of the elements are nodes. So node A, node C, and node B. So this is element 1 and element 2. Again, the degrees of freedoms are associated with the deformations of the nodes. So again, node A is clamped, so no degree of freedom. Node B, similar as above, has rotation angle. The middle point here, node C, it can display and it can rotate. So it contains 2 degrees of freedom. So to sum up, if you use two elements to model this beam, then you will end up with 3 degrees of freedom. So the slope deflection methods follow the following step. First, you have to identify degrees of freedom, like I just did. Next, you need to relate forces to degrees of freedom. And then you can solve for the degrees of freedoms using equilibrium. And then you can obtain forces from the degrees of freedom that you found from step 3. These are the 2 more examples to illustrate to you how do you select degrees of freedom. So for instance, this is a beam, hinge support and roller support. So I decided to use 2 elements to model the beam. Element 1, element 2. So node A, B, and C. So node A and B, they are supported. So they cannot move vertically, but they can rotate. So you will have rotation angles at A and rotation angle at B. At node C, this is a free end, so it's free to display and as well as free to rotate. So you will have displacement and rotation angle. So if you model the structure using 2 elements, 3 nodes, then you will end up with 4 degrees of freedom. So this is a frame structure. I apply a horizontal force, so the frame is going to display like this. So if I use 3 elements to model the frame. Element 1, 2, and 3. Then I will have node A, B, C, and D. A, D are clamped, so no degrees of freedom. B is free to display as well as rotate. So displacement will be along the horizontal directions, but not the vertical direction, because we assume they are actually inextensible. Node C, again, you can translate, but you cannot move vertically. It can also rotate. Also, you assume actually inextensible for this element. So the displacement at B should be equal to displacement at C. So to summarize, I will have rotation angle at B, rotation angle at C, as well as translations of B or C. They are equal. So I will have a total of 3 degrees of freedom. Next, I will show you how you can relate forces to degrees of freedom. So take this structure as an example. Take a segments out of the structures. This structure is subjected to external loads, and the structure is going to deform. The length of the segment is L. At the two cross-section A and cross-section B, there will be internal forces, including bending moments as well as shear forces. But if you know the bending moment, you can calculate the shear forces through local equilibriums. So let me temporarily neglect the shear forces. Just keep the bending moment acting on this segment. So in the next derivations, I'm going to assume that I follow these sign conventions for bending moment and rotation angles. If they are counterclockwise, I assume them to be positive. If they are clockwise, then they are negative. So I want to show you how you can relate the bending moments to the deformations at node A and B. So this is the segments under external force, and this is the deformed configurations with end moment of MAB and MBA. So such a condition can be considered as a superposition of two conditions. The first condition is I want to bend the structure into such a deformation shape using the end moments. The end moments are MAB1 and MBA1. So that's condition 1. Condition 2 is without introducing further deformation to your segments, I want to calculate how much additional member is needed to resist the external force. So this is assuming that both ends of the segments are now clamped. So the end moments will be introduced by the external force solely, without creating additional deformations. So it is assumed that this original condition is a superposition of these two scenarios. Scenario 1 is to deform the segments into such a deformation shape using the end moments. The second scenario is without causing additional deformations. I calculate the end moments required to resist the external force. So this condition is the superpositions of these two scenarios. So if I can only analyze these two scenarios separately and superimpose them, then I have this original conditions. So I'm going to show you one by one how I can achieve the slope deflections methods. So the first task is to produce moments such that it can deform the structure into such a configuration. The deformed configuration is quantified by deformations at point A, theta A, and rotation angle at node B, theta B, as well as rigid body rotations of the deformed configurations, which is 5AB. So I want to relate the end moment MAB1 and MBA1 with the degrees of freedom, theta A, theta B, and 5AB. So how can I relate these two sets of parameters? Assuming that I have a simply supported beam, I apply an end moment of M1 at the left end. I can calculate the rotation angle at left end and right end. I can establish this relationship through Castigliano principle. Next, I can do the same thing, but now applying the bending moment M2 at the right end of the beam. Again, I can establish the rotation angle theta12, theta22 respect to M2 through energy principle. I can superimpose these two cases. So I have bending moment M1 apply at the left and bending moment M2 apply on the right. And the rotation angle is a superposition of theta11 and theta12. So I can establish this relationship. Next, I can perform a rigid body rotations for this structure, tilting the right-hand side upward by a rigid body rotation angle of 5AB. So this is theta1, theta1. This is theta2 and theta2. This is the rigid body rotation angle. By doing so, it does not create additional bending moment into your structure. So based on the previous established equations, I can substitute the relationship. Theta1 is equal to theta A measured from the horizontal lines to the tangential line of point A. So this is theta A. So theta1 is equal to theta A minus rigid body rotation angle, while theta2 is equal to theta B minus rigid body rotation angle. So substituting these relationships into the expressions, then I can set up these two equations. So M1 is equal to 2EI over L, bracket 2 theta A plus 1 theta B minus 3 times rigid body rotation angle, 5AB. On the other side, M2 is equal to 2EI over L, 1 times theta A plus 2 times theta B minus 3 times rigid body rotation angle. So with this very straightforward derivations, I can establish the relationship between the end moments and the deformed configurations of your segments. So here is a summary. So I want to establish the relationship between the end moments and the deformed configurations. The deformed configuration is characterized by rotation angle at A, rotation angle at B, as well as a rigid body rotation angle of the segments, which is simply the straight line connection between the point A and point B after deformations and measuring from the horizontal line. So the result shows that the end moments are related to the deformations through these two equations. Note that throughout the derivations, we assume that we follow these sign conventions, where bending moment and rotation angles are assumed to be positive if they are counterclockwise. So we have accomplished the first scenarios, which is relating the end moments to the deformed configurations. And we say that the original relationship is equal to the first scenario plus the second scenario. So the second scenario is even easier. Second scenario is you are trying to calculate the end moments due to external force without creating additional deformations. Such a scenario is called fixed end moment. And we expected that we can pick up the fixed end moment from a fixed end moment table, which is readily available. So this is from the lookup table. Now, there are two cases of fixed end moment I would like you to remember. First is a fixed end moment corresponding to a midpoint concentrate force. So if you have a concentrate force applied at the midspan, the fixed end moment is PL over 8. PL over 8. According to our sign convention, this PL over 8 is positive. This PL over 8 is clockwise, so according to our sign convention, is negative. The other conditions I want you to memorize is fixed end moment for uniform distributed loads, W. So the fixed end moment for uniformly distributed loads is WL squared over 12. WL squared over 12. On the left is counterclockwise, so it should be positive. On the right is clockwise, so it should be negative. This slide summarizes the slope deflection methods. So we have derived two equations relating external force, internal bending moment, as well as the degrees of freedoms of your segments. So these two equations are MAB, which is the internal bending moment at the left end of your segments, is equal to 2EI over L times 2 times theta A, rotation angle at A, plus 1 times theta B, rotation angle at B, minus 3 times rigid body rotation angles of the segment, which is a straight line connection between the two deformed nodes and measuring from the horizontal line. And then at the end of the equation is a fixed end moment, AB, which can be obtained from a lookup table. MBA, which is the bending moment at the right-hand side of your segment, is equal to 2EI over L times 1 time rotation angle at A plus 2 times theta B, which is rotation angle at B, minus 3 times rigid body rotation angle. And again, at the end of the equation is a fixed end moment, BA, which can be obtained from the lookup table. Note that the rigid body rotation angle can be related to the relative displacement between A and B. So this is the rigid body rotation angle. So it is equal to the relative displacement between A and B divided by the length of the segment. So note that we should follow assigned conventions for bending moment and rotation angle. They are defined as positive if they are counterclockwise. So once you relate the forces to degrees of freedom, the next things you can do is to solve for the degrees of freedom using equilibrium. After that, you can obtain forces from the degrees of freedom. We'll illustrate these methods using some example in the class.